A 133-pound woman in a swimming pool expels air from her lungs and then has a density just barely greater than that of water. If she makes no effort to swim or tread water, she will slowly sink to the bottom of the pool. By taking a deep breath of air, she is able to float with her nose above water. What volume of air must be inhaled if 3% of her body's volume is above the surface of the water? All right. Well, let me start with a sketch. So there's the water surface, and here she is floating. A small percentage of her increased volume is above the surface of the water, 0.03 times V naught plus delta V. Delta V is the amount by which the volume of her body is increased with the breath, and so delta V is what we're solving for. And then underneath here, 0.97 V naught plus delta V. And in terms of a free body diagram here, we have her weight, 133 pounds. I'm going to convert everything to newtons here so we stay in System International. And then a buoyant force here, which is equal and opposite to the weight. Okay, so the buoyant force is the weight of the water displaced by Archimedes' principle. And so that's simply going to be the portion of her body underwater, which is this volume, 0.97 times V plus delta V, V naught, times rho sub W, the density of water, times G, and that is going to be equal to W. All right, now I want to solve for delta V, but I've got an equation here with two unknowns in it. I've got V naught and I've got delta V, so I need another equation. The rule, of course, being that the number of equations has to equal to the number of unknowns. So the other equation we have is this statement that she just barely has a density barely greater than that of water. So what we're going to assume is that her density is equal to that of water. There's really nothing else we can do. So for that to happen, her weight divided by her volume, her initial volume, before she takes that breath, is going to be the mass density of water times G. Multiplying by G converts kilograms per cubic meter to newtons per cubic meter, which is what units we have on the left side here. And so now I have my two equations, and now I can solve for delta V. So the only other thing we should do maybe before we start is to convert the weight of 133 pounds to newtons. And that's very simply done with the conversion factor. 4.45 is roughly the right factor, newtons per pound. And that gives 592 newtons. Okay, so using this converted into newtons now allows us to solve for V naught. So we can solve for V naught. V naught from the second equation is equal to her weight divided by the density of water times G. So that's 592 newtons divided by 1,000 kilograms per cubic meter, density of water, times the acceleration of gravity, 9.8 meters per second. And that turns out to be 6.04 times 10 to the minus 2 cubic meters. Okay, so from this equation right here, we can solve for V naught plus delta V, this equation right here. So I'll draw an arrow. We're going to come down now and solve this equation. And this gives V naught plus delta V is equal to W, 592 newtons, divided by 0.97 times the density of water, 1,000 kilograms per cubic meter, times the acceleration of gravity, 9.8 meters per second. So V naught plus delta V, it computes out to be 6.23 times 10 to the minus 2 cubic meters. You notice that this is a little bit bigger than that. The amount by which these two is bigger is delta V. So delta V is then 6.23 times 10 to the minus 2 cubic meters minus 6.04 times 10 to the minus 2 cubic meters, and that is equal to 0.19 times 10 to the minus 2 cubic meters, which is 1.9 times 10 to the minus 3 cubic meters. That converts to 1.9 times 10 to the 3 cubic centimeters. Remember, there's a factor of 10 to the 6th in converting cubic meters to cubic centimeters. So multiplying 10 to the minus 3 times 10 to the 6th gives 10 to the 3rd. 1,000 cubic centimeters is a liter. And so that is 1.9 liter. 1.9 liter breath that she inhales. Okay, so now a couple of assumptions here. I'm ignoring the weight of the breath that she takes, and that's probably enough to say.